In our first application of vectors, I wanted to try sort of a bit of a classic and emphasizing the importance of perpendicular coordinates. So let's take a quick look. Bob and Jane go camping, put their canoe into an 80-meter wide river. So this is the river. And they can walk with a speed of 3, right? So this is walking with a speed of 3. And they can also paddle with a speed of 3. Right? So this is their speed on land and on water. So this is land, and this is where they start. And they're trying to cross the river. So this is the perfect campsite right here. Okay, so Jane says that they should angle the nose of their canoe into the current. Let's see if I can find a little something to represent a vector here on my desk. Right. Here, let's do. Okay, just use this little bit. All right, so in Jane's method, what she wants to do is, keeping in mind the river's flowing this way, that they should angle the canoe like this and paddle, 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 like that, going across the river. So, yeah, it's definitely a possibility, and we can think about it. So I'm going to put that as Jane's method over here. Okay. And then Bob says the best way to do it is just to point the canoe directly across the river like this. Like, why mess around with this whole angling thing? Just point it straight across. Of course, they're going to get washed downstream because there's motion happening in 2 directions at the same time, which is the whole point of needing vectors in order to do this. And then once they get here, then they can just walk back. Okay, but in Jane's method, they're not going to do that. And the current is 2 meters per second. So we'll add that. Everybody knows water is blue, so I'll draw that 2 meters per second. Okay, great. So let's carry on with Jane's method, and then we'll do Bob's over here. Okay. So in Jane's case, she is talking about using the velocity of the canoe, which is a vector, and using that to neutralize the effect of the current. So that's 2 meters per second. And this is 3 meters per second. And then this is their resulting speed across the river like that. So it's slower than the 3 meters per second, but then they don't have to worry about being washed downstream. So this is going to be the velocity in the x direction, which is what they're looking for. Okay. So there's no acceleration in either direction. So this is just distance equals speed times time. But for the Pythagorean theorem, we can reverse engineer that to find out what Vx is, because we know that 3 squared is equal to the square root of 2 squared plus Vx squared. Okay. Whoops. I don't need that square root sign. Oh, let me just backtrack. Sorry. 3 squared is equal to 2 squared plus Vx squared. Okay, so we'll carry that forward. So this is going to be 9. It's equal to 4 plus Vx squared. So 9 minus 4 is 5. So Vx is equal to the square root of 5. So 2.24. So this is the speed with which they're going to cross the river. And the distance is 80. So x equals vx times time. And so the distance is 80 equals 2.24 times t. We divide both sides by 2.24. We get 35.8 seconds. So that's her time to cross. Now also, while we're here, let's consider what the angle is going to be. So we can tell her what angle to steer. So when we do try and find the angle, we go inverse tangent of y over x. And it doesn't matter, like, whether the velocities or forces or distances or what. So that's going to be inverse tangent and 2 over 2.24. So a little less than 45 degrees. Okay, so 42 degrees. Now let's come over and take a look at Bob's method. So Bob says, well, we're gonna take our velocity vector and we're just gonna, boom, just pound it right across the river, because that's the fastest way to get across. And he's actually correct about that. And then we'll have to add the 2 meters per second. And so their resulting velocity is going to be at a downward angle. And the resulting speed that they're going to get is going to be equal to three squared plus 2 squared. So their speed is, so that's 9 plus 4. So that's 13. Okay, so 3.61. Which is faster, for sure, than this 2.24 that we got over here. All right. So that's what we get. We get 3.61 meters per second. And we can now think about what the distance traveled is going to look like. So let's do the same thing. Let's make another vector diagram, but now let's consider what the displacements are. So this displacement is going to be 80 meters. And we don't know what this is. Whoops, lost my color coding. Oh no. Okay, and then this is going to be some kind of distance in the y direction. And then we don't know what this distance is either. But the time to cross is going to be equal to, here's our distance and here's our velocity. So time to cross, time is going to be equal to distance divided by velocity. So x divided by px. And so that's going to be equal to 80 divided by 3. And so it is a faster way of getting across the river. But the premise was that they're trying to get to a particular campsite, right? So this is 26.7 seconds. And so we have to figure out how far down river Bob's going to wind up. So while Bob's paddling across the river is pushing the canoe downstream at 2 meters per second for this many seconds. So the y value that we're getting is going to be equal to the velocity in the y direction times the time. And so we just have to multiply this by 2. And that's 53.3 meters. So their walking speed is 3. So the walk time is going to be equal to 53.3 divided by 3. So I'll divide that by 3. And that's 17.8 seconds. So we're going to have to add that to Bob's time. And I get a total time of 44.5 seconds. Which is longer than the 35.8. Forgot to write in the angle. And by the way, let's take a look at what this angle is. So our angle is going to be equal to, and it doesn't really matter, it could be this angle or it could be this angle. Because what we've done is we've created the geometry term as similar triangles. They don't have the same dimensions on the outside, but all 3 angles are going to be the same. And there's a scale factor that goes between them. So the scale factor is time. I'll multiply this out. So we know that this value is equal to 53.3. And if I do the Pythagorean theorem, I can find out what the hypotenuse for that is. Okay, 96.1. Right, so if I multiply this times 26.7, I get 80. This times 26.7, I get 53.3. This times 26.7. Right, so our scale factor is just time. And then finally, we'll see what the angle is, just out of curiosity, because these 2 triangles look like they're closely related, just flipped over. But it turns out, no, not really. And I'll talk about why in a second. Yeah, it's a pretty different angle. So 34 degrees compared to 42. And why is it different? Well, when we're adding these vectors together or doing the river problem, there are these 2 approaches. Do you angle to try and compensate for this perpendicular direction, or do you just ignore it? And the key is that the 2 quantities that we're talking about, the motion along x and the motion along y, are independent of each other. So Bob's method is actually the fastest way to get across the river if you don't care where you wind up along the river, because all the velocity is directed to going across the river. So Bob's 3 meters per second is the leg of this triangle, but over here, Jane's 3 meters per second is the hypotenuse, and that's how come these 2 triangles are not the same. And then in the next video, we'll take a look at projectile motion, because in projectile motion, it's very similar to this river problem, except along the y-axis is accelerating.